All right, peeps, we're at the very last problem. This one, letter C, where it says the pH of the solution at the equivalence point. Oh my goodness. Well, when we do this, we are going through all the steps. And there's a little twist in there that I'll show you. And part of it does involve rewriting the equation. I'll show you how you can rewrite the equation. But really, you also don't have to rewrite the equation. I'll show you that part. And so, like all our other problems, following through the scheme, write a balanced net ionic equation. Then we'll do the stoichiometry because we are titrating a weak acid with a strong base. And then we'll do our ice table and we'll figure out the pH from there. So when we start off, our net ionic equation is we mix together. One draw. This H NO2 aqueous. It does not completely dissociate, so I cannot dissociate it here yet, and because it's a weak acid. Plus this strong base. Remember that KOH, we don't write it as KOH because it has this K. It's one of your solubility rules, which means that it completely dissociates. So we write it as K plus OH minus. Aqueous. Yields forward reverse reactions because we're dealing with a weak acid, and this potassium ion will appear over on this side. Even if it does combine with something else over here, it will still completely dissociate. So it's left as K plus. It is a spectator ion, so I'm going to leave it out just to begin with here. And then my OH minus is going to absorb a hydrogen. My acid is going to donate a hydrogen. And I'll get H2O, liquid, and NO2 minus aqueous. Okay. So here's my net ionic equation. I'm going to go through the whole thing with the stoich, even though we kind of talked through it, because we are at the equivalence point. There is that thing of that the moles of your acid equals the moles of your base. But we're talking about this is the acid and this is the base that we're mixing. And we're not talking about conjugates right now. This acid, this base, the moles are equal. So because I'm mixing those, we're going to do a BCA table, do our stoichiometry. And we said before how we calculated it out. Our moles of our acid was 0.00400 moles. And if you forget how we got that, go back to the other video and you'll be able to see that. And if these two things are the same, we are starting with this. And we're saying we are at the equivalence point. So this is at the equivalence point. And that's the conditions that we're dealing with. But we're going to assume that this completely reacts. This is not an ice table. We're not dealing with equilibrium right now. We're saying that this stuff's all going to react and we're not going to worry about water. We're going to assume that we did not have any of the NO2 minus to begin with. So our change, we're going to end up forming products and decreasing our amount of reactants. So it's minus X plus X. And then because both of these are considered my limiting reactant, they are co-limiting. We are at the same stoichiometric ratios. It only takes 1 mole of this and 1 mole of this to create 1 mole of this. We have 0.004 moles and 0.004 moles. These are both my limiting reactants. They will both be completely gone, and then I will end up with X as my product. But this X, it has to equal this 0.0040 because that's the way that this math works. 0.00400 moles of NO2. Okay? So that's going to be one of the key things is that our moles of NO2 minus is equal to 0.00400. And our moles of HNO2 is equal to 0, and our moles of OH minus are equal to 0. Okay? So that's kind of like what we're going to start with in our next part. I'm going to rewrite this equation though, because now that we're done with our stoichiometry, Now we're going to do our equilibrium. But the thing is that we don't have any of this stuff. We are starting with this, and this NO2. I'm going to flip this equation around because it might make a little more sense when we use it. I will come back to it though at the end because really you don't have to flip it around. I'll show you. But we're going to, because we're done with our stoich, we're going to go to our ice table because we're still going to be dealing with equilibrium. We have NO2, which is a conjugate of a weak acid, and it will end up affecting the pH. And so now at the equivalence point, we have NO2 minus aqueous. And that's what we're starting with. And that's going to interact with water, H2O, liquid. And because it's a conjugate of a weak acid, it is going to be in equilibrium, and it's going to form, this is now a weak base. It will take on H plus, and we'll get HNO2 aqueous plus OH minus aqueous. And notice that this equation is really just our first equation flipped around. And we really didn't need to rewrite it, but it might make this next part a little easier to visualize and see what's going on. And so we're going to set up an ice table. And we're saying that our initial conditions are when we have no HNO2 or OH minus, that's from our stoichiometry. Water we're not going to worry about. And our NO2, we're going to start off with NO2. But here's the other thing. Ice tables, it can be in moles or molarity, but you want to use molarity because then when we use our K expressions, our equilibrium expressions, those have to be in molarity. So let's just do it here. And that's the other part of the trick here because the molarity, it's not 0.004 moles. And to figure out the molarity, it has to be moles of whatever you're talking about over the liters of the solution. And that's the trick because the moles, we know how many moles that we're starting with. That's cool. Here's our moles of NO2. And that's what we're really trying to figure out. But the liters of solution, it has to come from both the acid and the base that were mixed together because now we're at the equivalence point. It had both of these things. Remember, we had 40 milliliters of this. And from our first problem, we said it took 20 milliliters of KOH in order to dissolve it, which means the liters of the solution, it's equal to 40 plus 20, which means it's divided by 60 milliliters. I need to convert that to liters. A lot of times when I do milliliters, converting it to liters, I need to do this for myself because oftentimes I will mix it around, I'll multiply when I should be dividing. And just a little thing just to keep in mind. And so we have 0.0600 liters. And so I had to do that because I am trying to figure out molarity, not just moles. And if I do this, now I end up with 0.0667 molar NO2. And so now this is the molarity that I'm starting with, 0.0667 molar. And because I have NO2, I'm going to form products. So it's going to be minus X, and I'll get plus X and plus X. So I have 0.0667 minus X, and then X and X. And so when they talk about, if you ever watch other videos and they talk about dilutions first, this is the part that they're talking about. You had this moles of acid and moles of base that reacted and made your conjugates, all that stuff, or made your products. But then when you're starting here now, you had to dilute it. You had to combine those volumes of the acid and the base in order to figure out the molarity. Now I can go back and use it in my KB or K expression, and that's the part here too, is that they give you a Ka value, but this is not an equation for a Ka. This, because they have OH minus, this is a Kb equation. So I gotta convert it. Kw is equal to Kb times Ka, or sorry, Ka times Kb. Kw is 1 times 10 to the negative 14th. It's equal to Ka, they told us it was 4.57 times 10 to the negative 4th times Kb. So when I solve for Kb, I get 2.18 times 10 to the negative 11th. And so for my Kb value, it's equal to concentration of HNO2 times the concentration of OH minus divided by the concentration of NO2 minus. And I'm going to put in my values at equilibrium. I have X for the concentration of HNO2, X for the concentration of OH minus, and then 0.0667 minus X. Because my K value is much less than times 10 to the negative 4th, I can assume that X is going to be negligible. And solving for X, I'll get X equals 1.21 times 10 to the negative 6. Make sure that you take that square root at the end. And because this is in molar, and this had to be in molar anyways, and this is our molarity. This is the same as my concentration of OH minus, but oh my goodness, now I need to actually convert that to pH. So my POH is equal to negative log of concentration of OH minus, negative log of 1.21 times 10 to the negative 6 molar. And I get 5.918. I think, right? 918. There we go. Okay. But that's my POH. I need my pH, which means I need to subtract that from 14. 14 minus that, I get my pH is equal to 8.082 at the equivalence point. So this is also why when you have titrations with a weak acid, you'll still get that titration curve that looks like this. But instead of a pH of 7, it's actually shifted up a little bit. And the pH of 7 will actually be down below, and the equivalence point will be a little bit above. Because that weak acid, the conjugate base that you form does end up forming back into some of these things. And so that's why the pH ends up shifting a little bit. And that's how we figure it out. And yeah, that's it, you guys. So that was fun. So that is a lot of pain in the butts. Just something else to keep in mind too is that this equation that we rewrote for the ice table, it is the same as the equation from the BCA table, from the stoichiometry. You can run with that originally with it as OH minus, or we said our HNO2 plus OH minus goes back and forth and gives you NO2 minus and H2O. You could use that. It's just sometimes when you use that, you got to make sure that OH still appears as or on top in your KB expression. So rewriting it this way just kind of helps out with that. But either way, it works. And your KB expression, OH is always on top. And so that was cool, you guys. And so hope this was helpful. Let me know if you have any questions. Have a wonderful day.